Okay.
Sir, the last thing we did was Mole's law, right?
Yes, malice is law. That's correct. The intensity thing.
Yes, yes.
Okay. So today we are now going towards superposition. In the first part of this chapter, we will learn about interference. Now, interference basically can be of two types. Number one, it could be constructive interference or it could be destructive interference. Now, for constructive one, you guys need to understand that if a wave basically is in phase with another wave, like they are identical, so let's suppose this one has an amplitude. Let me just move it a bit down, some more space. Okay. So this wave has an amplitude A, and this wave also has an amplitude A. So when you add these together or they meet at a certain point, what happens is that they are going to become bigger. The reason why they become bigger is that if you notice the crest of the waves meet with the crest and the troughs meet with the troughs, so they sort of complement each other. So then the net amplitude of both of these will become 2A. Do you guys understand that?
Yes.
Now they must meet in phase in order to do that. So why? Because when you say constructive, it means in phase. In phase is like the wave should be like 0 degrees, 360 degrees, 720 degrees, or that of phase difference. That's when they're gonna add into each other. Okay. Then we have the other situation. The other situation would be that there is a wave that's like that. Uh, ये थोड़ा and basically the wave that looks like this now needs. So then what happens is, although this one has like in a line, you could say amplitude as A, and wait, let me write it down. I'm sorry, but I'm a bit sick. Amplitude A, and this one has an amplitude negative A because, as you can see, the crests of this are meeting with troughs of these, and the troughs of these are meeting with crests of those. Is it clear? So when it basically goes through, they end up creating or destroying each other completely, and that's how we call this uh, destructive interference because the net amplitude now is going to be zero.
So this is what happens in the headphone question, right?
can draw this, please.
So can you hear me?
Yes, yes. Come again.
So this is the theory behind the headphones question.
Yeah, yeah, headphone cancellation. Yes.
Since spaces.
Yes. Mm. Give me a second, please. Okay. Now, when all this happens, this basically tells you about um, a principle that we follow, or these follow. That principle, so that principle is basically called the principle of superposition. So the principle of superposition states that when, so you guys need to basically remember the keywords in this, all right? So the first, I'm going to break it into two parts, but you can always write it in one go, okay? When two or more waves meet at a point, now here you have this keyword that must be written. The resultant displacement at that point is equal to, now the second mark starts, the sum of the displacements at of individual waves at that point. All right, kids. Now, in this one, the keyword in the second one is sum of the individual displacement, sum of the displacement right here. All right, so you guys need to write that in order to get the full mark for this. This is 2 mark definition. Any answers? Any questions? Please let me know.
No pressure.
Okay. Okay, should I go forward, please?
Yes.
All right. Now, basically, like this thing, superposition. Basically, this is the same thing. Like for example, if there is one wave, this is just an example to explain what it means. So there's a wave like this, right? And right now we can basically say this is 2a amplitude, and then there's another wave which looks exactly like this, but now obviously it has just one amplitude. So whenever they meet at certain point, the resultant wave is going to become sort of say this much, because they meet constructively. That means that now the amplitude is going to grow to 3a. So individually at each point you can add it up to get the resultant amplitude. This is what it means. So you can draw this and write this down, and then I'm going to go forward. Yes, kids. Done. Should I go forward now, please?
Yes.
So one of the results, say, of creating or of principal superposition is the formation of stationary waves. Now, stationary waves, which are also called standing waves, are a result of interference between two waves of number one equals frequency, number two equal amplitude, number three, these things will be asked from you by the way, traveling along the same line, number four, in opposite directions. All right, kids.
Yes.
Then I'm going to explain what it means. Hmm. All right then. All right, should I go forward now, please? Okay. Now, basically, a stationary wave is like this. It's created like this. So suppose you have fixed end like this, and you have a wire like this or a rope, and you start moving it up and down. So what happens is that when you move it up and down, it sort of creates a wave that goes in this direction, right? And then what happens is that once this wave reaches the other end, it gets reflected from the other end, and then a new wave you create from the other end. So basically, one wave is coming from here, one wave is coming from here of equal frequency and equal amplitude. And once they meet together, they basically create a pattern like this, sort of like this. It's basically going up and down and doesn't transfer energy. This is basically the way a stationary wave is created. Is that clear?
Yes.
Okay. Walaikum salam. Ji walaikum salam. Yes, Raza, I understand. So Raza's saying that basically, won't it lose some of the energy when it is reflected back? Yes, Raza, it does lose some energy, but if you're giving it like enough energy, then it does create a stationary wave. It's not like there has to be a fixed end from the other side. It can be one another person doing that as well. So that's how it works. Okay, Raza. Okay. All right. Now let's look at the properties of a stationary wave, see what they are and how they sort of create these up and down things. So properties of stationary waves. So property of stationary waves are like, so once, like suppose when the wave is created, show you that. So basically they look like this. Okay, okay. Now, I just want to tell you that the parts which are these ones that do not move, these are called nodes. This will be a node as well. This will be a node as well. We generally denote it with capital N, node and node. And the parts that are moving up and down, center of it between two nodes, these are called antinodes. And we generally write it with A, like that. Alright, kids, please write this down. Furkan, Fatima, Shazib, everything is clear. Tanya,
Yes.
good. Now,
Yes, sir.
we also need to understand what exactly is a node and an antinode. So, a node is basically, you can basically write that it's a point with zero frequency. It doesn't basically move at all and with no energy. It doesn't move at all. Whereas an antinode, it's a point with maximum amplitude and it has the maximum energy as well, like that. Now, if you look at a wave, which is like this wave altogether, like that. And it looks like this right now. So one part of it, I'm just taking it out. So from this part, you already should know that this is a node, and this is a node, and this is also a node, and these are antinodes and antinodes. So if you notice that between a node to node, if I check this part, you might realize that this whole thing is just half wave, right, from here to here. So I can say that basically a node to a node distance is half lambda. And then if you check the anti-node part, so from this end, if you go here and you go here, so all this part is also like a quarter and a quarter. That's half lambda as well. So we can say anti-node to anti-node is also half lambda. So first of all, you guys need to remember this. But then if you check the distance between a node and an antinode, which is barely a quarter, like that, just a quarter. So node to antinode to node or node to antinode are equal to a quarter of lambda. Now this is very important to later on when we're going to solve the questions, you should understand that. So please draw this and let me know if you have a question. Is that clear, everyone? All right. Asma, you getting everything, Imal?
Yes.
Okay. Seconds. I am coming in 1 minute. Please, you draw this. Alright, kids. Done. Should I go forward now, please?
Yes.
Okay. Now let's. Physics, ASA, I2, IG. Okay. So now let's have a look at how these two waves, like we've already done progressive waves, we're now going to look at how progressive waves are going to be are different than the stationary waves. Now, let's draw this first. Let's copy this. Wait. So, pretty bad. Okay. Now, what happens is in a progressive wave, it transfers energy. Suppose initially the wave looks like this when the time is equal to 0. So this is the start, okay? So when a quarter time period has been passed, so what happens is that a quarter wave energy is transferred like that. So the wave goes forward. Then in the next quarter, which is half time period, when 2 quarters are passed, this wave goes further forward like that. So you can physically see that the wave is transferring energy. In 3 quarters time period, then this wave would go like this. And in 4 quarters, which is one whole wave and one time period, it basically moves like that. Is that clear, everyone? This is basically a progressive wave.
Yes.
But in stationary waves, that doesn't really happen. What happens is that if you see a wave like this, and this is when the time period is 0, so this will be the node, this will be the antinode, this will be the node, the antinode, node, antinode, node. Because these waves stay stationary, they don't move. So when the time period becomes a quarter, so the maximum points, which are nodes, they come down, these go up, and they come down. So these create basically a straight line like that. There's no change in the position of nodes, Antinodes are still there, nodes are still there, antinodes, nodes, antinode, node. So it looks like it's just flat. When the time period basically becomes um, half the time period, so these antinodes keep on moving down, these go up, these come down. So basically, this sort of create a wave like this now. It looks super bad. Okay. Now, considering this, then the node stays where they are. Antinodes are only moving. Nodes are there. This is antinode, node, antinode, node. As you guys can see, that the wave in half of it, this portion of the wave has gone up. These two up portions have gone down like that. Now again, when 3/4 of time period has been passed, so what happens is that again these need to go up, this needs to come down back, this needs to go up. So they just form another flat line like that. Nodes are still there, antinodes are still there, nodes, antinodes, nodes, antinodes, nodes, like that. And then after like one whole time period, basically it just looks like this again, just like the first one. Nodes are there, antinodes are there, nodes are there, antinodes, nodes, antinodes, and nodes. So as you can see, it keeps on going up and down from antinodes. It doesn't transfer energy forward. And this is the reason we call this a stationary wave. Is that clear?
Yes.
Alright kids, please draw this and then let's see what you can do.
So you said that these are stationary waves then.
Yes.
So how come they're moving down and up?
Stationary means they don't transfer energy. They just keep the energy within themselves.
Okay.
All right, kids, do you understand everything? If you have any questions, please let me know.
Yes.
Okay, so tomorrow now, I'm going to explain why and how the energy and the frequency works in this. I'm going to write a few things, and then we'll move to some of the cases in this. All right. Have a nice day then.
Yes. Thank you, sir.
Bye.